Good evening, everyone. So, today we are going to start a new chapter which is about Fourier series. So, let us represent f of x as a naught by 2 plus summation a n cos nx plus b n sin nx. The series of this form is known as Fourier series, where we need to compute a naught, a n, and b n. So, power series we have already discussed, and you can see that the power series can represent continuous functions only. But we will see in this chapter that Fourier series has advantage that it can represent more general function with many finite discontinuities. So let us assume that the function f of x is defined over the interval minus pi to pi, and we need to find the value of a n and b n. So here we assume that the series 1 is uniformly convergent, or we assume that the function f of x is uniformly convergent, so that the series can be integrated term by term from minus pi to pi. Now let's see that how do we compute a naught, a n, and b n. Think of the series and see it. So if you see here, then f of x is defined from minus pi to pi. So try to integrate it from minus pi to pi, both the sides, and see what will happen. So if you integrate both the sides from minus pi to pi, then you will realize that the left hand side would be minus pi to pi f of x dx, and the right hand side simply becomes a naught pi. And why is it so? Because for the remaining term you will have the integration minus pi to pi cos nx dx, where the coefficient is an, and minus pi to pi sin nx dx, where the coefficient is bn. If you integrate it and put the values pi and minus pi, you will realize that this integration would always be 0. And this is why you will get a naught as 1 by pi minus pi to pi f of x dx. Please do remember the formula. Now how do we get a n and b n? So for a n and b n, for a n we multiply both the sides with cos nx, keeping n fixed, and integrate from minus pi to pi. So again you will realize that in this case, when you do something like this, then there would be term where you will have the coefficient of bn and integration sin nx cos nx. If you use these formulas and integrate it and put the values, then they will come out to be 0. And in case of an, it will become cos square nx dx. Cos square nx can be written as 1 plus cos 2 nx by 2. And from there, if you do the integration and substitute the values, then you will realize that your minus pi to pi f of x cos nx dx would be an, and this integration would be pi. So this is an pi, and from here you will get an as 1 by pi. So an is 1 by pi minus pi to pi f of x cos nx dx. The integrations were very easy, that's why I am not going into the detail. I have given you the formula, please do try by yourself. And similarly, if you multiply both the sides with sin nx, then we will have the bn, which is 1 by pi minus pi to pi f of x sin nx dx. We can substitute the value of a naught, a n, and bn into the given series. That gives us the Fourier series for the function f of x. So a and b n are called Fourier coefficient, and one is called the Fourier series of f of x. Now let's try some quick exercises. So first one says that find the Fourier series for f of x is equal to pi over the interval minus pi to pi by 2 and 0 when it is pi by 2 to pi. So just use the formula. If you are good in simple integration, then it's straightforward. So a naught would be 1 by pi minus pi to pi f of x dx. Now f of x is defined from minus pi to pi by 2, and 1 by pi is here, and its value is pi and dx. So if you substitute the values, then it simply gives you 3 pi by 2. For an, the formula is 1 by pi minus pi to pi f of x cos nx dx. Again, f of x is defined from minus pi to pi by 2 and f of x is pi. So it's simply the integration of cos nx dx. So if you integrate it, you will get sin nx by n, and if you put the limits pi by 2 and minus pi by 2, it will become 1 by n. Pi would cancel out. So 1 by n and sin n pi by 2 minus sin minus n pi. Yes, now I know that sin n pi is always 0 and sin n pi by 2 varies. When n is equal to 1, for example, it is 1. For n is equal to 3, it is minus 1. So 1, minus 1 and so on. So from here I can write down that a2n is always 0, because sin 2 pi sin 4 pi is 0, and when you put 2n, then sin pi sin 3 pi and they are also 0. Sin pi sin 2 pi 3 pi. So a2n is always 0, and a2n minus 1 is alternatively you have plus minus sign. So it is minus 1 raised to the power n plus 1 divided by 2n minus 1. This is how we represent the Fourier coefficients. Similarly, if you compute bn, then it is the pi would cancel out. So it is simply the integration of sin nx, which is minus cos nx by n with the limits minus pi and pi by 2. So if you substitute the values, it becomes cos n pi by 2 minus cos n pi, because cos minus x is cos of x. Again, depending on the values, you will have the different. So first let's write in a more simplified form, minus 1 raised to the power n and cos n pi by 2 minus, and this is minus 1 raised to the power n. Yes. Now for example, if n is 1, 3, 5 and so on, then cos pi by 2, cos 3 pi by 2, they all are 0, and I will have minus 1 raised to the power n. If n is 2, then you will get cos pi is minus 1 minus minus 1 raised to the power 2. And if it is 4, then you will get cos 2 pi, which is plus 1 minus 1. So 1 minus 1, 0. So there are three kinds of the values. One is 1, 3, 5 and so on. The other one is 2, 6, 10 and so on. And the last one is 4, 8, 12 and so on. For 4, 8, 12, it is 0. So we are not interested. For 1, 3, 5, I can write b2n minus 1 as minus 1 by 2n minus 1. N got replaced by 2n minus 1. Cos n pi by 2, for 1, 3, 5, it is 0. And minus 1 raised to the power 2n minus 1. Now minus 1 raised to the power 2n is 1. So that's why minus 1 raised to the power minus 1, that gives you minus 1. So minus minus will become plus, and there is already a minus, it becomes minus 1 by 2n minus 1. And for 2, 6, 10, I have minus 1 by 2n minus 1. And now cos n pi by 2. So it's cos pi, which is minus 1. And this becomes minus 1, because minus 1 raised to the power 2 times 2n minus 1. So that gives you 2 and 2 would cancel out, and it simply is 1 by 2n minus 1. So now you have all the values. So therefore you can write down f of x, which is a0 by 2. So a0 is 3 pi by 2. So 3 pi by 4 plus summation an. So an I got minus 1 raised to the power n plus 1, 2n minus 1, and cos, this summation is common, 2n minus 1x. Then bn. For bn, two values are there. One is 2n minus 1. So sin 2n minus 1x, and 2 times 2n minus 1. So I will get sin 2 times 2n minus 1x. So this is my required Fourier series. Yes, very simple calculation. Let's try one more question. I suggest you must do it by yourself. So here f of x is defined over the interval 0 to pi by 2 only. For others it is 0. So that's why the integration is very easy. If you verify, a naught comes out to be 1 by 2. An is 1 by pi, integration from 0 to pi by 2, and cos nx, which is sine nx by n. So this becomes 1 by n pi and sine n pi by 2. So you can see that if n is 2, it becomes 0, n is 4, it is become 0. So a 2n is 0. And for the odd values, you will get plus 1, minus 1 and so on. So 2n minus 1 pi, and it can be written as minus 1 raised to the power n plus 1. Similarly, if you solve for bn, then it becomes minus 1 by n pi and cos n pi by 2 minus 1. Again, there would be different situations. When n is, for example, 4, then it is 0 for the odd values and for the values 2, 6, 10. So b 2n minus 1 is minus 1, 2n minus 1 pi, and it is cos pi by 2 is 0, cos 3 pi by 2 is 0, so it only remains minus 1. So 1 by 2n minus 1 pi. And for b2, 2n minus 1, it is minus 1, 2 times 2n minus 1, pi is there, and minus 1, so it gets simplified as, now you substitute the values into the Fourier series, that gives you the required answer. So in the next class, we are going to talk about the convergence of the Fourier series, because we do not know that this right hand side would converge to the function f of x or not. So we have to see under what condition it would converge. Thank you.